Hey guys, I know it's been a while, but I'm still here trying to help out where I can. In the meantime, I have been supplying some of those links that hopefully you guys are taking advantage of, but I also know that sometimes they can be confusing as they don't necessarily line up directly with the slides or directly with the path that we are taking for this. So I'm trying out something new. I have a whiteboard in front of me, a couple of markers that I'm going to be using to follow more directly along with the slides that I'm supplying. So today we are kind of working still with those geometric sequences, geometric series, where we've already looked at the arithmetic series, and those are basically just addition. You could think of arithmetic as addition, where if we have a start, let's say our pattern is just adding 3, so we go from 2, we add 3 to get 5, we add 3 to get 8, and so on and so forth. That was our arithmetic series, but now we are working with geometric, where our pattern works around multiplication. So in our slide, we have a sequence being given to us that is as follows. We have 8, we have 24, 72, and 216. And this sequence continues on for quite a while. But we want to try and turn this into our geometric series, which uses our formula for it. If I remember correctly, our previous slide kind of looked into how that formula is found, and all you have to do is, very, very similarly to our arithmetic series, we are looking for a pattern. In this case, our pattern is some form of multiplication, and for this particular pattern, our multiplication is actually multiplying by 3, because 8 times 3 is 24. We then take 24, we multiply it by 3, and we get 72, and so on and so forth as we continue along. So now our pattern for multiplication is times 3. So we're going to hold on to that for now, because when you're doing all of these times 3, times 3, times 3, you basically end up with 3 times 3 times 3, however many times that you have terms. So in this case, if we follow along that pattern, when we take a number and multiply it by itself, no matter how many times we do it, in this case 3, that is the same as an exponent. So 3 to the third power, that is where we start off. In this case, we could just write 3 to the n as our term number. So then we just need to make sure that we are doing this correctly, because 3 times 3 times 3 is 27, but that's not what our number is. So we have to then multiply by our starting term so that we know that that is where we start off, because we start off as 8 multiplied by 3, multiplied by 3, and so on and so forth. So this becomes our formula of 8 times 3 to the n, where we are using n as our term number. So this is where we start off with looking into our formula. Now there is something important to note about this particular formula. So if we were to plug in 1 as our term, then we would have 8 times 3 to the n, and will notice that we turn n into 1, and that just becomes 8 times 3, which is 24. Now this particular formula does not actually start at 1, it starts at 0. So in this case, you could almost think of it as our formula being n minus 1, but there is a little bit of a reason why I'm not putting it as such, and we'll be exploring that in just a little bit when we are working with sigma notation. For right now, our main focus is just understanding both of these formulas, the one where it starts at 0 and a formula we are going to see that actually starts at 1. So our formula that's supposed to start at 1, we have to basically set it so that when we plug in for n, where we are not changing n at all, we end up with our value of 8. So in this case, for term 1, we would have to plug in 0 for this formula, so we have to work around that. We need for a fact that we have 3 to the n power. So we need somehow, starting from here, we need to end up with 8, where we are still using that initial term. So in this case then, 3 to the first power is just 3. So when we have 3, we need to somehow multiply that by an 8 being changed somehow to get 8. And what better way than having 3 as our denominator, because when we multiply these two terms together, the denominator 3 and the numerator 3 cancel out, and we get left with 8. Now, you might be a little confused. You might be wondering, well, why do we do that? Why are we trying to get this done? All that we take out of this explanation here is that if we want our starting point to be 1, we have to take our initial value, in this case being 8, and we have to divide it by our multiplier pattern. So we take our initial value, we divide it by our multiplier, and then we keep our 3 to the n. In general terms, we can consider that 8, or our very first term, is a, that our multiplier is r, and that n is just the term being used here. So n would be our term number, or perhaps not term number, just continuation number. So because here we started at 0 and here we started at 1. Make it our input. So this is the basis of what I want us to kind of make sure we kind of understand here, that of course there are always multiple ways we could write a formula, that in this case we could write the formula starting at 0 as just a times r to the n, where n starts at 0. And that will give us our first term, second term, third term, as we keep incrementing n. So at n equals 0, we would have 8. At n equals 1, we would have 24, and so on and so forth. While if we plug in our formula as follows, where we take a and first divide it by r, then multiply by r to the n, that is where n is equal to 1, and we are starting with 1 as our term. So in this case, rather than this being 0, we could just plug in as 1, we could just plug in as 2, 3, 4, and continue. I know this can be a little bit confusing, but that's why I'm focusing just on this part for now, where I know in the slides it does bring up the sigma notation, but that is as a kind of preparatory for tomorrow as we dive a little bit more into sigma notation. So now to just recap a little bit, you might notice a small change here where we still have that same sequence that we're working with from 8, 24, 72, 26, where we have our multiplier pattern as times 3. We still have a as our first term, r as our multiplier, but as we are turning into our sigma notation, I'm using k as our input, just because in sigma notation, if we remember, there is typically our sigma, and then we have n equals to some number as our maximum value, our maximum term. So in this case, I'm just changing k as our input, and you could see over on the right here that if we're starting at 0, then we just have our first term multiplied by our multiplier and our input, and if we're starting at 1, we have it as a over r times r to the k power. Now, in this case, as we're working towards sigma notation, if we remember our arithmetic series, our very, very base sigma notation for arithmetic series is we take sigma, we have some maximum value, and we have k starting at 1. And it was very important that k is starting at 1 because our base sigma notation is just k. And we were able to see that we have a formula for that, that if we want to get the sum of all of these numbers, we just take n times n plus 1, and we divide that by 2. Now, these formulas come into play and are very important when we are finding out that base sigma notation for a geometric series. Because from that base geometric sigma notation, we can get every other geometric series and just work with that. So we're just starting it here as a bit of a preview. We're going to be looking into it a little bit more tomorrow, but just to kind of get the mindset going about it, and I'm sure I will very likely repeat myself come next time for this again, but we need to have a sigma notation. We need to have a uniform set for it, a uniform starting value. In this case, since we're starting at 1, we're also going to start this sigma notation at 1, and then we have whatever our maximum value is. So in this case, since we're using it as a uniform set at k equals 1, we want this formula right here where we are starting at 1 as our number. So we plug this formula into our sigma notation, and from this formula, we are going to get from this sigma notation, we are going to get a formula that no matter what, as long as we know the values given here, we are able to find the total sum of everything without having to count up by hand or through calculator, because with geometric series, the numbers get very, very large very, very quickly. So in following along here, there are a couple ways to look at. I believe that the attached file I have, the attached link, goes into a lot more detail as to where this formula actually comes from. But our formula ultimately is that we take that a value and we multiply it by a numerator of 1 minus r to our maximum value, and a denominator of just 1 minus r. And this formula right here, for any of these values we have, will be able to give us our total number. So if we wanted to just kind of start off a little bit small, let's just say that our maximum value is 3. And then in our sigma notation, we are starting at k equals 1, and we're going to plug in the formula we get from this sequence. So our very first term is 8. Our multiplier is 3. And then we take that same multiplier and set it to the k value. So if we set this as 1, we should get 8. If we set this as 2, we should get 24. And now we just need to turn it into this above formula here, where we take our first term 8, we multiply it by 1 minus 3 to the n, which is the third power, and then 1 minus 3. And if we begin to do our simplification of this, we're going to leave our 8. The first thing that we might want to simplify is this exponent up at the top. 3 times 3 times 3 is the equivalent of 27. We're going to do 1 minus 3 here. And then we're going to continue our simplification where we take 1 minus 27 and get negative 26. Let me actually move that over to make sure we have the room for it. So now up top here, we're going to keep our 8, and we're going to start simplifying this fraction where 1 minus 27 is the same as negative 26. 1 minus 3 is negative 2. In this case, this fraction can be simplified much smaller. Both of the negatives, all that would happen with those is they would cancel out, making this positive. We would still have our 8, and then we could do 26 divided by 2, which is 13, and then we would just have to do 8 times 13, which I believe should be 104. Always good to double check. 3. Perfect. Where this would be the sum of the first 3 terms within our sequence. And of course, if it works for one of the smallest numbers, it'll work for some of the largest numbers as well. But again, if this isn't necessarily clicking right off the bat, mostly just focus on understanding that there are technically 2 types of formulas, and knowing that as we move into our sigma notation, we may not necessarily be starting at 1. We may end up starting at 2, 3, 4. But we need to know the very base formula for each of these in order to move forward, where for the arithmetic series it is n times n plus 1 over 2, and for geometric series it is our first term times 1 minus r to the n over 1 minus r. I hope this is helpful. I know this is starting to get much more confusing, and I'm going to be trying to keep on top of any way that I could possibly help you guys, whether it be something like this, whether it be just a really good link that I find. I'm hoping you guys can also help out as well if you happen to find something that was very, very helpful for yourself. Either let me know, see if you can maybe set it up in the stream, and if this is helpful, let me know. I'll keep it going. If it's not helpful, I'll see if I can maybe change it up, but I'm just trying to set something up so that it follows a little bit more closely to the slides rather than introducing new numbers and trying to then decipher which one is which. Otherwise, I do hope you guys are staying healthy and safe, and I hope you enjoy the rest of your day.